Hi class, welcome back to Electromagnetics. We've now looked at how electromagnetic waves propagate in different types of material. The three types that we define are conductors, dielectrics, and magnetic material. And we've solved Maxwell's equations for all of those and seen how that affects our electromagnetic waves. Now we want to consider what happens when we're traveling in one material and then at some boundary we switch to a different type of material. What happens then? In this lecture we'll look at that. So first, inspirational thought, Proverbs 22:28. Do not move an ancient boundary stone set up by your ancestors. Of course, I felt this was applicable because we're talking about boundaries, and this is the scriptures talking about boundaries. There's the connection there, but I think there's a lot of wisdom here in that, sometimes we see these boundaries that have been set up for a long time, and we think, oh, well, that's inhibiting, us or someone else, so we should move the boundary. When many times those boundaries were put there for good reason, and we need to understand the wisdom of why they were put there. So I think that's good advice in this scripture that we should be hesitant to be quick or not be quick to move boundaries that were set up by our ancestors. So again, continuing on in part 5, like I said, we've looked at the different types of materials: conductors, dielectrics, and magnetic materials. Any material that we want to propagate a wave in must fall in one of these three types. We've solved the wave equation and found a solution for that, and then we've looked at special cases in these materials. So now we want to look at what happens when we go from one material to another. So like I said, we've now examined how waves propagate in all these different types of materials. Well, what happens when we transition from one type of material to another? Or from similar material types with slightly different characteristics? What's going to happen? Well, we want to examine what happens in these cases and methods and make sure we can account for these changes. So as we've done in everything in this course up to this point, we want to start with Maxwell's equation. So like the title says here, Maxwell's equation again. We're going to keep coming back to that because these are the equations that govern what happens, and we can use them to analyze these situations. So hopefully we're getting comfortable with Maxwell's equations. And so we'll recall then our general integral form for Maxwell's equations. We have Faraday's law, Ampere's law, and then the two Gauss laws. Again, just saying the sum of the electric field around a contour is equal to the time derivative of the magnetic flux density of penetrating the surface of created by the contour. Same thing with magnetic fields with currents. And then we are looking at the sum of the flux density, the displacement current density is equal to the amount of charge in a volume, and then the flux density should always sum to 0 through some surface created by a volume. So for our boundary, let's think about this. We're going to have two mediums, a medium on top and then a medium below, and we're going to have a plane boundary in between them. So this is the boundary between medium 1 and medium 2. And so we're going to find this rectangle that's normal or orthogonal to this boundary, A, B, C, D. So the top half, of course, is in medium 1, the bottom half is in medium 2. And so AN is the unit vector normal to the boundary plane, and AS is the unit vector normal to our little rectangle here. So if we now apply Faraday's law to this rectangle and let the rectangle shrink to 0 by taking that limit, what we'll have then is the limit of AB, AD, BC, as this whole thing goes to 0, summing up the electric field around that rectangle, that should equal to the limit of the time derivative of the flux density penetrating that. So as this rectangle shrinks to 0, the above equation then will reduce to this equation here. All it will have left is the sum of the electric field across AB in one medium, and then E, the electric field going across CD in the other medium. And then over here, since this is going to zero, this area is going to zero, that flux density will go to zero. So we can rewrite that then as just this electric field evaluated at this point AB minus the electric field evaluated at this point DC, and that should equal to zero. And again, where B goes to zero is the area goes to zero, and E is simply measured at these 2 points, these 2 single points in each medium. So we can now define, again, AS to be the unit vector normal to the area ABCD. So we talked about that before. So again, AN is normal to this plane, AS is normal to this rectangle. And then if we use the right-hand rule of direction of advance, this vector and the unit vector normal to the boundary are then defined graphically below. So we're going to utilize that on the next slide. So with these unit vectors defined, we can now better define our equation to say that the 2 unit vectors cross product, and then that'll be dotted with these 2 vectors here. So that'll give us those 2 tangential components, shall we say. So rearranging this triple product, which we're allowed to do, we looked at the first couple of weeks. If you have a triple product like this, something cross something dot something, that you can exchange those 2 operators and not change the result. So as we do that, we notice that since ABCD is in any plane normal to the boundary, so any plane normal to this AN, we can rewrite this then as, because those 2 dotted together will just give us AN, and so this is our new equation here. And so we can actually rewrite this in scalar form by applying this cross product to say that the tangential component of the E field in medium 1 minus the tangential component of the electric field in medium 2, the difference of those should always equal to 0. Again, where ET are the tangential components of the electric field. So again, this means that the tangential components of E fields in different mediums at any point on the boundary must always be equal to 0. So this is our first boundary condition that we were able to derive from Maxwell's equation. This is always true regardless of the mediums, the medium types, what's going on. These electric fields on each side of the medium, their tangential components have got to be equal. Their normal components do not, and we'll deal with that later. And so we can't really come up with a set rule for the boundary conditions for the normal components, but the tangential are always equal. So just as we did with Faraday's law, we can now do the same thing with Ampere's law. So again, for this rectangle, we're going to take the limit and shrink this down using Ampere's law. So we're measuring the magnetic field around the contour of our rectangle. And then we're going to shrink the area down and keep measuring the current and the displaced current, time differential of displaced current. So as the rectangle shrinks to 0, this above equation then will reduce to this. So again, we're having the tangential components here, and then we're having the current as it's crossing our differential surface times the AB component. So we can rewrite that as this, just the magnetic field evaluated at the points. And so here our displacement goes to 0 as the area goes to 0, and the magnetic field and the current density are simply measured at 2 points crossing the area. So again, we can incorporate these unit vectors to define the equation above. So we've got our normal to our boundary, and this is normal to our rectangle, and again our magnetic field in medium 1 and medium 2, and then this is again the surface, what's crossing this normal surface, the current crossing this normal surface. Again, we can rearrange this triple product as we did before, just interchanging the dot and cross products. And finally, since we know that these will always be normal, this gives us the final vector form of the boundary condition. or in scalar form. And again, this is important. We have the tangential parts or components of our magnetic field. The difference in those two must always be equal to the current flowing across our surface. So the difference in the magnetic fields at the boundary, tangential components of the magnetic field at the boundary, they've got to be equal to whatever current may be flowing on that surface. If there is no current flowing, then they're equal, of course. But if there is any flowing, that's going to account for the difference in these two. So again, these are the tangential components of our magnetic field. So this means that the difference, again, in the tangential components of the magnetic field in different mediums at any point on the boundary must be equal to the amount of current flow on the surface. So this is our second of 4 boundary conditions that we're going to derive using Maxwell's equations. Note should be taken here, though, that this one can be problematic since the direction of the current flow is not always well defined, especially in relation to the magnetic field. So this one can be a little bit tricky. You've got to keep up with your directions here, as that can play a part in that. All right, so let's look at this again, another boundary setup. The previous boundary setup was for Faraday and Ampere's law, so this is our second boundary setup for Gauss's laws. And so with this one, as we hopefully become accustomed, instead of dealing with a surface, we're going to deal with a volume. So we're going to set up again, we have our medium 1 and medium 2 and this plane boundary between them. This is normal to that plane, this unit vector here. And so we create this rectangular boundary. So A, B, C, D, E, F, G, where half of it is in medium 2 and the other half's in medium 1. So now if we apply Gauss's law for electric fields to the rectangular box, and again take the limit to let that shrink, so we're going to sum up the displacement current density vector on the surface of this box. It should be equal to the amount of charge inside the volume, and again we're going to let this surface shrink to 0 or approach 0. So as we let that happen, what we find out then is that the normal component of our displacement vector in medium 1 and in medium 2, if we add those together, they should equal the total amount of charge on the surface. So we could rewrite this then to say the normal component of the displacement vector in medium 1 minus the normal vector, the normal component of the displacement vector in medium 2 has got to equal to whatever charge may be present. Of course, if there is no charge present, then they have to be equal according to Maxwell's equations. So again, this is the total charge on the surface, on the border between these two, and dn are between the two mediums, and dn is the normal components of d. So as before, we can incorporate that normal vector, and we can write it in vector form this way or scalar form this way. This is our third boundary condition. It means that the difference in the normal components of the displacement current vectors in different mediums at any point of the boundary must be equal to the amount of charge on the surface. We don't have any relationship that always holds for the tangential components, but just the normal components. So again, this is our third boundary condition, again from Maxwell's equations. So finally, we're going to apply Gauss's law for magnetic fields on our rectangular box. And as we do that, again, we're summing up this flux density on the surface of the box, and Maxwell's equations, or Gauss's equation, tells us that should always equal to 0. So as we let the box shrink, it comes up that the normal components on each side, here if we add them together, they must equal to 0. Or we can rewrite that before as the normal component in the medium 1 minus the normal component in medium 2 is always got to be equal to 0, which means they have to be equal. Again, where these are the normal components of our magnetic flux density. So as before, we can incorporate this normal vector as follows, and then this gives us this relationship. And so again, what this is telling us is that the normal components of our magnetic flux density fields in the different mediums at any point on the boundary have got to be equal. So this is the fourth and final boundary condition that we were able to derive for any boundary using Maxwell's equations. So now we put all these results together and we can characterize what's going on with an electromagnetic wave propagating along and when it comes across any boundary. And so this is the general form of what's happening there. So this will tell us what's happening with the electric field or certain components of it, components of the magnetic field, in relation to the current, in relation to the displacement current, in relation to charge, and then the magnetic flux density. Of course, we can rewrite that in scalar form, which kind of makes a little more sense to us. And this just says that on any boundary, the tangential components of the electric field have always got to be equal. The normal components of any flux density on a boundary have always got to be equal. The tangential components of any magnetic field on this boundary have got the difference between those have got to be equal to any current flow. And then finally, the displacement current at any boundary, the normal components between those two, the difference between them has got to be equal to the charge on the surface. So these are pretty handy, and we'll look at an example of how this helps us to figure out what's going on at the boundary and beyond. So this is a pretty handy little graph here that helps us see what's going on. So we have medium 1, and we have this boundary, which is a solid line here, in medium 2. So we can see that the tangential components, that is, components that are going tangential to the boundary of the electric fields, have got to be equal. Now you could have components going in other directions. Again, there's nothing that states that that's always got to have some certain relationship, only the tangential parts. Same thing with our flux density. The normal components have got to be equal on each side of this boundary. You may have tangential components or other components, nothing there that says that has to have any type of defined relationship. The magnetic fields, again, they are going to be equal except for the difference of whatever current flow there might be. So the difference in these two is going to be equal to the current flow. And finally, with the displacement current, they'll be equal with the exception of whatever charge may be on the surface. So that'll explain whatever differences there are between those. So again, some pretty handy relationships that we can utilize to characterize what's going on at any boundary. So if we now consider the boundary between two dielectric materials, we know that in this case that the conductivity, which affects the current density, which is equal to the electric field times the conductivity. Those aren't equal per se, but they're all related and they all equate that in a dielectric they will be equal and that they'll all be equal to 0. So this gives us a special boundary case condition. So in this case, everything's just equal. So the electric field's tangential components have to be equal because this is equal to 0. The magnetic tangentials have to be equal. The displacements have to be equal, and the flux densities have to be equal. So that's a pretty special condition. So if you have two dielectrics going from one dielectric to another and a wave's propagating through it, the wave should travel through at least these components of it unhindered. Likewise, another medium we might want to look at, two different mediums. That of a perfect conductor. We know in this case that no time varying field can exist in this medium, therefore we can modify the boundary conditions as follows. We can see here then that the normal vectors times these have got to be equal to 0. This has to be equal to any current flow and any charge on the surface. So what this means then is the electric field must be totally normal and the magnetic field totally tangential on all surfaces when we're dealing with perfect conductors. So if the electric field is totally normal, that would imply that you're having current flow through these surfaces, through these boundaries. So let's look at an example. So in this example, we're going to start with a perfect conductor, and then at this x equals 0 boundary right here, we transition to a perfect dielectric, which in this dielectric the permittivity is double free space. And then at this x equal d boundary, we will transition from this perfect dielectric into free space itself. So you can see the permeability of there's no magnetization that we're experiencing here. We're only experiencing change in the polarization because our permittivity is changing. So with this configuration above, we're given this electric field defined by two components. It has an x component and it has a z component. So the x component is going to go in the direction of normal to the boundaries. The z component you can see here is tangential to the boundary. So this is the tangential component and this is the normal component to our boundaries. Likewise, we have a magnetic field. It's defined in the y direction, so it would also be tangential. Of course, one's tangential left and right. The magnetic field is tangential going in and out of the board or the paper here. So what we want to know is what is the current density and charge on the surface at x equals 0, and then what is the E of the electric and the magnetic fields at this surface here. So let's take a look and see if we can use our boundary conditions to help us with this. So the first question is about the current and the charge at x equals 0. So at this point, the charge at x equals 0, we can find that by taking our boundary condition, saying that this normal vector dotted with d1 is going to be equal to 0. So our d1, remember the relationship between our electric field and our displacement vector is by multiplying by the permittivity. So we know that in that first boundary, that permittivity was 2 epsilon naught, or 2 times the permittivity of free space. And we know that the normal vector is ax in the x direction. So when we plug those values in, and this was already going in the only component of the electric field that's going to contribute to this, then because of this dot product, because if we dotted ax with az, that's going to be 0, so the only component that's going to contribute is this one. And so when we multiply that out, we get 2 epsilon naught E1 sine 2 pi z. So this would be an equation that describes how the charge behaves. It's not static charge. You can see the charge is changing. It's going up and down. Likewise, our current density at x equals 0 is going to be the normal vector with cross product of our magnetic field from our boundary condition. Again, that was from Ampere's law. And so in this case, again, our normal vector will be ax, and we're going to cross that with our magnetic field. And so here's our definition of our magnetic field. So when we cross ax with ay, that gives us az, and multiply that out, and you can see that the current is basically the same, are related to our magnetic field in that sense. And so we have to take into account that this is at x equals 0, so when we put that x in here, our cosine of 0 is always 1, so that's what happened to the cosine function. And so here is an expression for the current density on that surface. So what about the second part? What is the electric field and the magnetic field at that other boundary between the two dielectrics? Well, we have to remember that our tangential components have to be equal. And so in this case, that would be the EY components. Or excuse me, EY components are equal to 0 because there is no EY component. But then the other type of tangential, because remember, x is in the direction of going between the boundaries, so z was tangential to the boundary. So our z's must be equal, so our tangential component of our electric field in both mediums is just this E2 sine pi times whatever d is, cosine 2 pi z. All right, so that gives us that. And then we can find the other component. Here's kind of the tricky play, right? So we can find the normal components, or the dx components of our displacement vector from Gauss's law. It says that they're going to need to be equal. And so we know what that is, right? It's 2, at least in the sandwiched medium, it's 2 epsilon naught Ex. So, because the x component's the only part that's normal. This part, we don't know what the relationship on the boundary is, but we know this normal component, what it'll be. And so that becomes 2 epsilon naught E1 cosine pi d. So we put in d for the x value, sine pi z. And so we have our tangential component and we have our normal component here. Because we can get our normal component of our E field. Remember, the constituent relationship is they're related by the permittivity. So since we were 2 epsilon naught in the middle medium, when we go to the new medium, we have to account for we have our displacement vector, but to get our electric field vector, we have to multiply by what the permittivity is. And when we do that, that's when we come up with this new value here. So again, we have our z component, we have our x component, so this is our tangential component and our normal component for our electric field. So therefore, we can recombine these to get what our electric field is going to be just on the other side of the boundary, between the second and third boundaries there. So again, it has an x component, which is our normal component, and a z component, which is our tangential component. So now if we, since they're two dielectrics, if we let our current equal to 0, we can see then that our our tangential components in our magnetic field have got to be equal, and then our normal components have to be 0, or this other potential tangential component is 0 because there is no z component for our magnetic field. So this gives us our tangential component here, the only one, that gets the only contribution. So now if we use Maxwell's equations, Gauss's equations from Maxwell's equations, we know that the normal component of the flux density has to be equal. So therefore, our magnetic field just across the boundary has got to be equal to the same magnetic field on the other side of the boundary. The only way that they might have differed would have been if the permeability had been different on each side, just like it did with the electric field. Since the permittivity was different, it changed the values as they crossed the boundary. So, hopefully that makes sense. You go back and work through this again, just applying these boundary conditions. So you have to kind of play with it a little bit to see how to get all the components of each field so you can redefine them on each side of the boundary.